Hello, I'm Dave Loope. I'm a geologist at University of Nebraska, and I'm very pleased to be celebrating the 25th anniversary of the Grand Staircase-Escalante National Monument. My talk today is about the processes that chisel sandstone into beautiful landforms as they turn solid rock into loose sand. My colleagues on this project are Jim Elder, Vitaly Zlotnick, and Garrison Loope. There's a huge volume of rock exposed in the Grand Staircase, but a much larger volume has been broken down and carried away already. In the last 10 million years, about 300,000 cubic kilometers of rock, sandstone, limestone, and shale, have been removed from the Colorado Plateau as it's slowly uplifting. All the rocks in the chocolate, the vermilion, the white cliffs, the gray cliffs have been eroded away. They were all deposited where the Grand Canyon is now, and now their remains are at the bottom of the Gulf of California. The Navajo Sandstone is about 1,000 feet thick in the monument and about 2,000 feet thick at Zion National Park. Here's the Navajo Sandstone along Highway 12, and here is the sand produced by the breakdown. The arrow shows the direction toward the Colorado River and the Gulf of California. So this stuff is on its way. This is being worn away. All right. If I'm going to talk about the Navajo Sandstone, I have to tell you about cross-bedding. And this sketch up here shows you how sloping layers form within migrating sandstones, migrating dunes. And this photo shows you a very small portion of an ancient dune that 200 million years ago in the Jurassic was migrating southward, in this case from right to left. But more importantly, to our purposes today, there's a much, much younger living crust of lichen on this rock, on this erosional surface. And this lichen is preventing the breakdown of the rock under it. You can see from the flakes here that this is not protected by lichen, and it's under attack. This is a sheeting joint, and you'll be hearing that word pretty often in the next 20 minutes or so. It's a low-angle fracture, and they're very common in the Navajo Sandstone as well as in granite in particular. So, millions of people visit Yosemite National Park every year. Why? Obviously, it's because it's one of the best places in the world to see sheeting joints. And I use the word daylighting here. This fracture, they all formed in the subsurface, down in the rock. And now this fracture is seeing daylight for the very first time. Underneath this slab is the same fracture, but it's still back and in the dark and not yet to bask in the sun. So this is a daylighting sheeting joint. The sheeting joints are much more widespread than that. So this is just a line, whereas there's a plane underneath this rock that has been opened during fracturing. Okay, so here's a cross section. Let's call it Yosemite Valley. Here's Half Dome. That last image was of Half Dome, and it showed that Half Dome looks kind of like the innards of an onion. It's got layers in it. They're not depositional layers. They're layers that are they're sheets of rock separated by sheeting joints. So the valley itself is about 1 million years old. The sheeting joints are forming right now, so they're very, very young. The granite is about 100 million years old. The fracturing that's taking place now is the result of the stress, the compressive stress. It's the same stress that's moving the whole continent of North America from east to west right now. It's a moving plate, and therefore the rocks in the subsurface are under stress. But when the rocks are near the surface, this arrow here becomes very, very low stress. Whereas here, there's a lot of gravitational stress from the overlying rock, as well as the compressive stresses like here that relate to the plate tectonics. So sheeting joints can't open until the rock is very near the surface and the gravitational stress is low. Then it can pop off and become separated from the underlying bedrock. All right, you're seeing sheeting joints in the Navajo Sandstone now. And remember, they're always younger than the rocks they cut. The crossbeds here are sloping to the left, and that's all one big set of crossbeds, all deposited within a single giant dune. Might have been 300 feet high. So this right here is not covered by lichen, but this is, and this is. So all these surfaces are protected. And if we know that this rock is breaking down into sand, where is it happening? Well, one of our conclusions is that it's happening right along these surfaces, right above the daylighting sheeting joints. So that's a step that connects a protected slope, and it's connected to the underlying slope as well. So much of the surface that you see, that you hike over, is not breaking down, but the whole rock unit is slowly wasting away due to what's happening here. Here's another view, and here's a step. Here's a lichen-covered surface. The step up is facing the down slope direction. Here's the next one, the next protected lichen-covered slope, and there's another step, another slab that's on the top is protected by lichens. And you see this going on and on and on. One thing that does change is on the very low slopes, like this, the daylighting sheeting joints are widely spaced. But up here on the steeper slopes, and there's lots of daylighting sheeting joints there, but they're all crowded together. Now, remember this butte, it'll show up in the map in the next slide. So here's that butte, and the white lines are showing the position of daylighting sheeting joints. The little beads on each one of those shows you the downslope direction. So I showed you one in the last slide that was facing downslope. Here's one, here's one. So that's the typical thing. They are typically perpendicular to lines of drainage. And notice here's another butte with a closely spaced daylighting sheeting joints, and here's a ridge that has the same look, and another one here. All right, what we're seeing here is, there's another, this is an exposed sheeting joint. And so so what I'm telling you about the lichen-covered surfaces, they were once covered by multiple sheets of rock, but those sheets have wasted away, exposing these surfaces. So they're exposed sheeting joints. They formed in the subsurface. They're not in the subsurface anymore. And you can trace this one along here. So it's concave up. And remember that sheeting joints form parallel to the land surface, like at Half Dome. They were very steep on the bottom of Yosemite Valley. They were almost horizontal. So this sheeting joint is a line of drainage for modern streams. You get a heavy summer thunderstorm, water will come flowing through here, maybe a couple feet deep. Okay, and so here are the sheets of rock, and sheeting joints are seen on up this slope and on this slope as well. The erosion along this wash by the moving water can cut through the rock, and it can cut through a whole slab of rock, and that then generates a margin to that slab that will become a point of rock breakdown. Here's another valley. Flash floods come around the corner here and right through here. There's an incision into the rock here. But this side of the valley is loaded with sheeting joints, all of which are parallel to that land surface. There's 14 sheeting joints right in here, all parallel to that slope. So here's our main idea, and it is that these rocks are being torn apart. They are disappearing. The landscape is being eroded down. That's called down wasting. But if you look a little closer, you can see that individual slabs of rock, sheets of rock, are back wasting. They are retreating up this slope. So that's their path. They may start in a situation like this where running water will cut through a slab, and then that margin will start here, and it will slowly through time move up the slope. And why does it do that? It's being broken down largely due to infiltrating water that's moving parallel to the sheeting joints. So the rain and the snowmelt are entering the rock and moving vertically, slowly under the influence of gravity, but when they encounter an open sheeting joint, they are redirected laterally so that they're moving along. They don't cross the sheeting joints. They can't jump that gap in the rock. And so that makes the water kind of focused on this area right here. The green lines are the lichen-covered surfaces. There's one, and here is where the action is. Notice that this is a convex up series of sheeting joints, and it's steep here, and that's because the sheeting joints, as they get further and further to the left, they slow down because there's not as much water that can get in and contribute to the breakdown of the rock. As you go up the hill, at the top of the hill, there's very little water focused there, whereas down here, a lot of water is delivered. Another thing is the action of gravity. So you've got a stack here of rock sheets, and that slows down the breakdown of the rock. I'll be showing you later that the rock is broken apart. It's torn apart by freeze and thaw, and the forces that are generated by freezing of water in the pore space, that can be pretty significant in a situation like this. But up here, where there's more gravitational force keeping those grains together, it's not as effective, and that's what causes the stacking here on these highlands. Here we see 3 ridges and 2 swales. There's a ridge, and there's a ridge. The swales are just out of sight. That's where water flows. That's where erosion takes place. So the series of events here is at one point, pretty far back in time, two streams running parallel start to cut down into the Navajo Sandstone, and soon thereafter sheeting joints start to form, and they form along the same orientation and steepness as the stream cut valleys. And so through time, more and more of the rock is eroded away in a very distinctive manner, involving the sheeting joints, and water continues to flow in two streams through the swales. Now here's a ridge top sloping to the left and to the right. Good chance to see the cross beds up close and how the sheeting joints cut them at a high angle over here, but over here they become nearly parallel to the bedding, and therefore become hard to see, and maybe sometimes it's hard also to see if they're there or not. Here's an interesting case where we've got a rock tower, and on the sides of the rock tower there's almost a dozen sheeting joints. There's one, there's one, there's one, there's one, there's one. At the top of the tower is the capstone. This is an iron oxide cemented part of the sandstone, and at some point in the deep past, this blob of sandstone was surrounded by regular sandstone. It got cemented by iron oxide, and when erosion time came, this was much more resistant than the surrounding rock. So what we have here is a history of about a dozen migrations of individual sandstone sheets. There's another one down here that's not yet visible, but the margin, the down slope margin of that will migrate up this slope, and that same sheeting joint goes under the tower. And as that margin comes up here, it will erode all the rock. All the rock around will be destroyed, but the platter of rock underneath the tower will add to the total height, the relief of this tower. So how many more migrations of these slab margins will take place before this tower collapses, falls over? Hard to say, but it's an interesting case demonstrating the importance of the migration of where the slab is back wasting upslope. Here's another example of the same thing. Here's a young slab that's almost reached the tower. That's a thick unit there, and thinner, but another close to a dozen sheeting joints were involved, and one mass of iron oxide cemented sandstone. So the slope of the land is recorded by the slopes of the sheeting joints, so that the rock there has been a ridge for a long time. This has been near the crest of the ridge for a long time, and that's made visible by the orientation of these sheeting joints. All right, what's the mechanics of this breakdown process? Well, we wanted to find out. The freeze and thaw thing, is that really right? We bought some sensors. They're not cheap, and these sensors can record the temperature of the rock, but that's cheap. But the expensive thing is they can also record the amount of water that's in this porous and permeable sandstone. So when it's completely dry, 25% of the rock is air. If it became saturated, it'd be 25% water. We have two sensors and a data logger, and this lower sensor, sensor number 2, is pushed through lichen. The needles go down into the rock vertically, and in this sensor they go in horizontally, into the rock that's not protected by lichens and is almost vertical. Here's the data set from December, January 2020 to 21. We started the monitoring. We installed the sensors in August, hoping to get the Arizona monsoon. No, we got a non-soon. So this snowfall was the first precipitation that was recorded at our site. The temperature shows that these are daily cycles. So 24 readings a day, and you can see that the temperature got up into the 70s on some of these winter days. But each night, the rock got down below zero, so that when the snow came and the snow melt came, water went down into the rock. Both sensors recorded incoming water. More got into the vertical sensor than into the horizontal one, but both got water. And so through time, there was a slow reduction in the amount of water. It started out maybe a little over 20% water. That's close to saturation, and it got down as low as 4 to 5%. Evaporation is the long-term process that removes the water from the rock. But what's removing the water from the rock there and there and there? Remember, we're talking about liquid water here, and in this case, the liquid water is disappearing and the solid water, ice, is taking over. What the sensor is sensitive to is it's called permittivity, and it's a dielectric phenomenon, capacitance, and water has a much stronger effect on the electromagnetic field than ice does. So you get a lower value when the ice starts to accumulate. But anyway, here's a nice snowmelt event recorded. Lots of water went in, and the water underwent nightly freezing and daily thawing. And that's a recipe for breakdown of rock. Here's another record from March of 21. And this was, here's the snowstorm, the snow melt. And once again, the water goes into the vertical face, the upper rock sheet, and it also goes into the lower rock sheet, the blue line there. More water goes into the red than into the blue. Maybe that's due to the lichens slowing the route of water into the lower sensor. And finally, we wait long enough, we get the Arizona monsoon, a nice thunderstorm, a series of them, and here again, a lot of water goes into the upper sensor, but not as much into the lower one. But, yeah, not just not as much, but virtually no water goes into the lower sensor. Apparently, the water fell too fast. It did not have time to infiltrate through the lichen-covered rock. And this is direct evidence of that. So it looks like even though water gets in the summer, because there's no freeze and thaw, that water is sort of going to waste. It's not really having a big effect on the breakdown of the rock. And so a big part of our learning is that winter is the time to develop the conditions that lead to breakdown of the rock. And this leads to the idea other people have suggested that some of the landforms on the Colorado Plateau developed during the Ice Age. When ice came all the way down to Des Moines, Iowa, it was up in Washington State and Idaho, in the mountains of the Rockies, and Lake Bonneville covered much of Utah, got 1,000 feet deep. The climate of the Colorado Plateau almost certainly was cooler and wetter. Some interesting studies that use pack rat nests have shown that the vegetation changed with a cooler, wetter climate. So the breakdown and back wasting of the Navajo Sandstone, it makes sense that it was probably faster under these conditions. So we see the processes, the important processes going on today, but that doesn't mean that the rate of rock breakdown is the same now as it was in the geologic past. And in conditions like this, it was probably much faster. So here are the conclusions. Sheeting joints and lichens control the evolution of beautiful landscapes. Large portions of the outcrops are colonized by lichens. They colonize the exhumed sheeting joints. And the margins of the rock sheets, the steps, are slowly moving up slope. They're back wasting as the rock's broken down. In winter, the snowmelt infiltrates lichen-covered rock, but it doesn't do that during the summer. So nightly ice crystals grow, prying the sand grains apart and breaking down the rock. Process probably more rapid during the Ice Age. Thanks a lot for your attention.